Good afternoon.
Good afternoon. Hello, hello. And I want to hear all about it, but right, not right now, obviously. But hello. And good sorry. Good afternoon, Jenna. Well, good afternoon, Justin. Good afternoon, Jenna. Thank you. Good afternoon, Alyssa. Good afternoon, Erin. Good afternoon, Eileen. Awesome, awesome. Still going. Wait, I'm still. Good afternoon. Yes, and thank you. And it is matter of funny. Right. Sorry. Yes. Good afternoon, Yabo, and good point. I'm going to go back. Good afternoon, Sheeran. Welcome back, so to speak. Yes, want to hear about that? Well, I don't want to hear. But anyway, yes. Okay. Good afternoon, Marissa. See, it's happening. Just what I was saying. All right. Good afternoon, Marissa. Good afternoon, Wen Yi. Good afternoon, Rachel. Hello, Alinelli. Oh, yes. Okay. So hello, everybody, and hello, other people that are coming in right now. But yes, totally legitimate question in the direct chat, which I'm happy to answer. Well, first of all, yes, thank you for the reminder about the FBDs. We actually are going to do the FBD thing today. We're going to, so yes, and in fact, I think we're going to do it first. So, but good. Thank you for remembering to remind me. And then as to and good afternoon, Kimberly. Awesome. As to a question in the private chat, which I hope which I do mean to have, I do not mean, so there's a question in the private chat that I do not mean to be a mystery at all. Actually, I'm not saying the person's name, but I'll just read it because the person is wondering if the final exam would be administered like the midterm, or if it will take place during an allotted time in the final exam schedule. Oh, wait, and more people are coming. Sorry. Fair question. I hope I have definitely not been trying to play hide the ball with that, but the more I look at that question very particularly, I can see how even some things I've said about that may not have fully satisfied that question. So let me answer, but people coming in, hold on a second, but I do want to answer that. Hang on a second. I mean, and basically anything about the final, of course, is very fair and reasonable concern. And I think there's still some loose ends that I have to get back to you guys. But yeah, so about the final, I mean, we're not going to get too deep into the final today. But yes, as far as the final exam is concerned, on the one hand, yes, in every way, shape, and form, it will be administered. So this is for anybody who's listening right now, or for all of you. And I don't mind saying this again as we get closer. But the final exam, oh, and someone else is coming, sorry. Okay, the final exam, well, maybe I should. Okay, well, the final exam, and again, I'm just saying, anybody who's coming in right now, I'm saying something about the final exam right now just because somebody just asked, not because I'm trying to get anybody all fired up about it right now. Like, we're not doing anything about it directly right now, but the final exam will be, oh, and someone else is here. Okay, how come okay, hold on. Okay, oh, okay, sorry. All right, I'm going to pause for a second. But good afternoon, Kimberly. Great to see you. Good afternoon, Andre. Great to see you. Awesome. And good afternoon, Sarah. Sorry about that. Great to see you. Okay, I think that, and people are still coming in. All right, I'm going to just pause for a second so I don't keep stuttering and say. But yes, for people who have been sitting here patiently, the agenda for today is once everybody's here, I'm going to quickly just address the final exam, just because I guess we are getting close and someone did just ask. Then I want to do a few minutes on the free body diagram thing. And then I want to get back to Doppler effect, which is where I more or less you are in lab, or certainly is something that is on the final. Okay, I think everybody's in here now. So yeah, so regarding the final exam, again, today is not a day that we're dealing with the final exam in a big way or very explicitly or anything like that. But again, about the final exam, just because there was a question, it will be conducted or administered or formatted just like the midterm, in that it will be take home. You will have many days to do it. You will be allowed to use any resources you want in order to do it. You will get some sort of practice document with some sort of solutions before it. I mean, we might be a little bit more, there might be less time. You might have less time with that practice document. And there might even be the solution set that you get for that document might be less complete than last time, but I can tell you, but it will be the same kind of, you do it however you want to do it under whatever conditions you want to do it kind of thing as last time. It'll be the same standards. And yes, now here's the specific question that was asked. And you will know what's on it before it happens. Like the main purpose of the practice document you'll get will be to fully explicate to you exactly what you can expect on the final. And it will be the case that if there's anything on the practice exam that we don't fully answer, I mean, if we don't give you a full exact solution set or something, if we don't give you answers to something on the practice exam, then that is a guarantee that that thing will appear verbatim in the final exam, if that makes sense. So it's the opposite. So I hope that makes sense. But so in all of those ways, it will be the same as the midterm and the same grading, GRADIN, the same standards of grading as the midterm. Like you have to present us with a document that makes every question super explicit. We have to be able to grade your document without looking at anything else. We have to know that you understand what the question is. So you can't just cut and paste our question, but you have to put the question in your own words, all that stuff, all the same. But yes, now as far as timing of it, because I really think this is what really was the import of the question in the direct chat, the timing will be that you'll have the final exam period to do it. In other words, and don't hold me to the exact minute to minute of what I'm about to say. I mean, but conceptually, what's going to happen is we'll post the final exam like pretty much on the last day of classes or right after the last day of classes or something like that. And in one way or another, either in your last lab period or in your last period with me, somehow we will address questions about the practice exam before all classes end. So the actual exam will be posted pretty much on the last day of classes, something like that, or the Thursday of that week, which I think is the last day of classes, and then it'll be due back pretty much on the last day of the final exam period. Again, I might be slightly off here by like a day on one side or a day on the other, but the concept is you're not doing that. Or maybe we'll even post it slightly earlier, to give you more time to ask us questions or something, but I can't promise that. But what I'm really trying to say conceptually to everybody is that you're not going to be working on this exam during class periods or class times or the class part of this year. You will pretty much have the full final exam period to do this exam, almost as though it were like an English essay or like an American history paper or something like that. And it'll be due pretty much on the last day of exams. So if final exam period is essentially a week, then you'll essentially have a week to do this. So to be even more clear, if I can, and of course we're going to talk about this more. We will talk about this more. I'm only saying it now, again, for anybody who just tuned in, so to speak. I'm only saying this now because somebody asked, and it's a fair question. And I guess I'm also saying, because we're getting close, and I can also tell you that when we get back to the Doppler effect discussion today, like definitely Doppler effect is one of the things that will be on this final exam. I can also tell you that there will be a circuit problem on this exam. Wait. Okay, wait, I'll look in the chat in a second. So, and so like I'm saying, pretty much this will be posted at the end of all classes. So the practice exam would probably come up essentially a few days or a week before then, but I know that's almost like now, I know. So everything's a little bit of a press right now, but I can tell, but the Doppler effect problem that I'm going to raise with you today in class, which will be hopefully very, very reminiscent to you, very familiar to you from something that Wu did with you, like that will be one main section of the exam right there. Like the part of the exam will be a Doppler effect problem, much in the spirit of what Wu will have done with you and what I will address today. I'll look in the chat in one more second. What am I trying to say? Now I just lost what. But yeah, all right, let me look in the chat to see if I've and I hope and the person, and maybe even if the person who did, again, sorry, I'm just a little bit thrown off by other things right now, but I think it's a legitimate question, and I just wasn't prepared to talk about this today because we have other things, but I will talk about this again as we get closer. Like, I don't want the final exam to be a mystery or something, but if maybe the person who did put the question in private chat, if they could just privately tell me whether I've answered their question or not. I just want to make sure, at least, to the extent I can right now, but let me look in the chat. Yeah, I mean, so the practice exam, I mean, okay. Oh, cool. And is it all the same person? Okay. Cool. Yeah, I mean, so the practice exam will be soonish. I mean, ideally, we would give you the practice exam like a week before classes ended, around there, or maybe a week and a half. But I know we're already getting so close. I may have already blown that, but the practice exam will be soon. But again, I can tell you the final exam will be one big circuit problem, one big Doppler effect problem, and one other problem that I'm not yet discussing, just to give you an idea. But yes, and it'll be the same thing as always, like have all the equations in it, and you can talk to everybody else. But just know the grading will work just like it did on the midterm. And the grades, as you know, were all over I mean, it is very possible to do very, very well on an exam of this format, but it's also possible not to. So just, approach it the exact same way you did the midterm if you did well. Okay. Hopefully okay, great. So hopefully that answered. Okay. So the main topic for today will ultimately be Doppler effect, but right, as you've reminded me, which I appreciate, and as I've sort of promised, I just want to spend a couple of minutes on free body diagrams. And please, again, all right. So hold on a second. We are recording. Okay. So we're talking about free body diagrams right now. This is, again, just because I feel like I think there's still some confusion or something that was demonstrated on the midterm exam. This is like to the side of the curriculum. This is just fundamentals of physics that go back to beginning. This is not a criticism or anything like that, but just as far as your note taking or your organization of thoughts, like this is a little bit of a sidebar here, but I've just been promising it for a while. So please take notes and just put them wherever and just bear with me, please. Okay. I'm going to turn the page in a second. We're just reading this. So in a free body diagram, just to remind you, and this part I do think everybody understands, but the whole thing of a free body diagram is we take an object of concern. And in classical mechanics, that means we take a particle of concern. We take an object, we focus all of our attention on what really is the center of mass of that object. But in other words, we choose one Euclidean zero-dimensional region of space, one dot, one point that somehow represents the entire mass of the entire object. So it's a point that's usually near the geographical center of the object, but specifically is at the center of mass of the object. We isolate that one point of mass. We picture it at what's happening to it at one point in space, at one point of time. So this is a very specific thing. We're not, and again, just like in an experiment or just like when taking a partial derivative or something, we're not asserting that there is only one point of mass, and we're not asserting that it only exists at one point in time or space or anything. We're just focusing all of our attention on one particular point in time, one particular point in space, and what is happening to a particular point of mass at those coordinates, right? So so free body diagram sort of means we're about to draw a diagram of this body free of any other distractions or any other variables or any other objects, really. Okay, so we focus all our attention on this one dot. Tell me if you need to go back to that page, right? And we draw a dot representing it, and then we draw one vector right? So before I go, so we're going to use a dot to represent the point mass, right? Or to represent the particle, to represent the point, which represents the particle, i.e. the point mass. So we draw a dot. And then what we're going to do, what we always do in a free body diagram, what we're trying to do is we're trying to account for all forces acting on the object, right? Not any force that the object is exerting on anything else in the universe, not those, although they always exist. And they're very relevant, but that's not what we're putting in the diagram. What we put in the diagram is every force that is acting on our object, i.e., we're accounting for every interaction. We're accounting for every single influence on our object coming from any and every other object in the universe with which our object is interacting. Right. Okay. I mean, I guess that's also sort of straightforward, but so we are drawing one arrow for every force that acts on our object. And the arrow that we draw as a vector, we place the tail at our dot, and then we orient the tip of the arrow in the direction that the force is actually acting. Still, I think people do get this as a concept. Okay, I mean, I'll draw it on the next page, but we're going to represent our object with a dot, and then we're going to put in an arrow for every force acting on the object. But let's keep in mind, like the whole point of this, or the whole perspective on this idea of a free body diagram, and it really is, the free body diagram is not just a rough sketch. The free body diagram is a computational tool, an explicit computational tool, just like vectors are. That is to say, we believe in the free body diagram very strongly. We believe that if we actually drew it like to some degree of scale, if we chose a scale for drawing these free body diagrams, and we scaled our arrows appropriately to that choice of scale, we actually believe two things. One, that by actually measuring, drawing out these arrows and measuring them precisely, we could actually use the measurement of these arrows to actually discover something numerical and quantitative about ultimately the acceleration of our object. Two, we actually believe we are not drawing arrows to give a rough idea of what we've already figured out. We draw these arrows to enable us to figure something out. And it took me years and years to realize this, but diagrams in physics are that way. They are not after the fact sketches. They're not just for communication between the drawer and the reader. They are actually a computational tool. And remember, a lot of our computational tools actually come from a time in history where we literally didn't have, let's say, calculators, right? So they are calculators, these things. They are not to show anybody else what you already know. They are to enable you to know something. And that's why they actually are, in some ways, harder than they look, because you actually have to take the rules seriously, but they're also easier than they look. Free body diagrams are like the answer to the question that's often asked in physics, or the complaint that's often made in physics. Like, I kind of get what's going on in physics when people go over it, but I never know how to start, right? Like, this is how you start, is the free body diagram. But okay, hello, that was weird. More specifically, what the free body diagram is really for, it's a tool for enabling us to solve F net equals ma, to apply F net equals ma to a situation. And F net equals ma never goes away in physics. Even when after Einstein we come up with cases where we subtly say, oh, we think F net equals ma isn't complete, or like there's more to be said about the world than F net equals ma, or even like technically it's like you could even say wrong in some weird case. But even when people are saying that, they're still referring everything back to it. It is the foundation of physics problem solving, like into the 21st century, for real, or the whatever century we're in now. The 21st. And F net equals ma says, if you know all the forces acting on an object at a given instant and in a given point in space, then you necessarily know the instantaneous acceleration of that object. And once you know the instantaneous acceleration of an object, then it all goes back to chapter 1 of physics. Like, then it's all, x equals 1/2 at squared, or x equals v squared minus v naught squared over 2a, or like all these equations with a in them. The whole premise is we're trying to predict where things will be when, and the whole way we make those, or we're trying to do forensic physics, so we're trying to retrodict where things were back when. Either way, the whole underlying principle that connects past, present, and future of motion is always acceleration, the rate of change of motion of an object. So the whole idea is that we spent this, anyway, I don't want to get too bogged down, but we spend a lot of time the world, not just this class, but we spend a lot of time trying to like really understand what we mean by acceleration and developing all these equations, and more specifically, developing the differential calculus that enables us to actually picture and believe in the idea of an acceleration existing at one point in time and one point in space. Like, acceleration is the second derivative, right, of position with respect to time. A lot of the work we have to do at the beginning of physics is just developing the mathematics so that we can even believe in the right side of F net equals ma. A lot of the beginning of physics is all about really believing and understanding what's happening on the right side of that blue equation I just wrote. a lot of the slog of physics, a lot of the stuff that you guys may well not like or get sick of, or get a lot of the calculus prerequisites you have to take, and then a lot of the kinematics equations that we slog through for months at the beginning. It's all about packing and unpacking what we mean by A. Because once we really believe in and understand A, then we predict, then we use A to predict and retrodict everything we want to know in physics. But Newton comes along and says, yeah, it's all about A. It's all about A. It's all about the second derivative. All the action in physics is about the second derivative, not the first, because the first derivative, velocity, is just in the eye of the beholder. Like I can get too bogged down in this if I'm not careful, but first we develop a notion of rate of change. We do all this math and all this vocabulary and all these equations to really understand how it could be that we could believe in a rate of change in a moment, like how something could be changing when no time is passing. That's the idea of a limit. That's the idea of a derivative. That's the idea of velocity, all this stuff. And that's hard enough. But just when we think and then we get from math the idea of once you understand rate of change, you can take a rate of change of a rate of change. And you can take a rate of change that's partial with respect to this variable, not that variable, like all this stuff. That's all about rates of change at a moment. What the math says, you can do that at any level you want. There's rates of change, rates of change, rates of change, right? And you're seeing this all the time. And there's rates of change with respect to space, and there's rates of change with respect to time. And those are all the details that we're seeing in the wave equation and all of those abstractions. But first and foremost, what physics says is, you know what? That's all math. Math allows you to take rates of change at any level you want. But physics says, we focus our attention generally on the second rate of change. Notice even, and again, not to confuse people, but to try to keep this alive for everybody, even in all the crazy stuff that we're doing with the wave equation, as hard as it looks, right? It's a partial differential equation that has derivatives going on both sides of it. But notice on both sides of the wave equation, as advanced as we've gotten in physics, we're still focusing our attention on second derivatives, not first and not thirds, second derivatives. Why is this? It's because I'm telling you, it's a rhetorical question, but I'll answer it. Why second derivatives remain the heart and soul of physics, and second order differential equations remain the heart and soul of physics, no matter how deeply and far we progress? And even Schrodinger's equation. I'm sorry, I'm really getting myself, but I'm just sort of desperate to show you why free body diagrams actually matter, I guess. Even Schrodinger's equation, which you have to struggle with a lot in PChem if you haven't already, and in instrumental and in higher level quantum mechanical scenarios. Schrodinger's equation, which is super important but possibly one of the more intimidating things that ever happened in physics. If you stare at that thing long enough, you even start to realize, oh my God, that is just a second order partial differential equation, very similar to the wave equation. That's what it is. And another reason I care so much about the wave equation. If you can really get the wave equation, you'll be much more prepared for PChem if you haven't taken it yet. But why? Why is everything a second derivative all the time? Why is everything second order differential equations? Because F equals ma. Because what Newton is saying is first derivatives, velocities, rates of motion, they look interesting at first. It seems like that's what we would care about at first. If you would seem like if you know how fast something's going, you'll know where it will be when, and that's true. But speed, velocity, first derivatives, they're all relative. This is Galileo. The Earth, how fast is the Earth going? Well, it's going 0 relative to me, but it's going 65,000 miles an hour relative to the sun, but it's going 650,000 miles an hour relative to the center of the galaxy. And the center of the galaxy is going at God knows what speed relative to the center of the Vega supercluster or whatever the heck we're in. I think that's right. Velocities are totally dependent on frame of reference. And you never, ever, ever, ever feel a velocity, right? You never feel a constant velocity. That's why you can go in an airplane and go to sleep and complain about the movie, if you know what I mean, right? Or you can be in an elevator and space out, while you're in the middle of the elevator journey from the bottom of the building to the top, because you don't feel velocities, because F doesn't equal mv, F equals ma. What we feel what we feel are changes in velocities, the result of forces, right? Okay, so like that's so long. I'm just trying to put this all in perspective, but then that means if we believe Newton's second law, which in a way in English just says in the physical world of space and time, the action is on the second derivative. Like if you want to know what's happening in the world of space and time, always pay attention. Like the in the physical world of space and time, when objects interact with each other, when one object comes along and pushes or pulls another, what it does is it changes the velocity of the other. Forces accelerate. Well, net forces accelerate. So our program becomes, I mean, it did become last semester and it remains. The program is if you know all of the forces acting on an object at one instant of time and at one position of space, then you know the instantaneous rate of change of position with respect to time. Like if you actually know at one moment, again, these are derivatives, right? In the limit as we go to, as t approaches zero, if you go to the limit, if you look at a point in time and a point in space and look at all the forces acting on a point of mass at that infinitesimal swath of space-time, if you were to know all the forces acting on an object then you'll know how that object will accelerate then. So it's super important for us to be able to know qualitatively and quantitatively what are all the forces acting on an object at a given moment, at a given point in space and time. In other words, okay, again, I'm saying like, I'll do it mechanically in a moment, but the real purpose of a free body diagram is to give us a full accounting of the entire left side of F net equals ma, so that we know what to plug in for the left side, and then we can get out something on the right side. Now, before we go any, so first what we do is we draw a free body diagram according to the instruction I just wrote here on the sheet. Like we draw a dot. Like in the center of our page. And let's see. Okay. Again, it's like, as long as I'm doing this, as long as I'm going to spend time doing this, I guess I want to be as explicit and clear as possible. So I keep trying to rush it, but there's no point in me rushing this. If I'm going to do this, let me do this right. So what I'm saying is, please understand. So again, for anybody who just joined, this is like my review or refresher or re-instruction on free body diagrams. So the first thing I want to make clear right now is this thing that I just drew in brown right here on the sheet. This is a picture. This is not the free body diagram, right? So I'm using an example of somewhere where I'm going to draw a free body diagram. and of course I'm taking this example from the midterm because I think there was a lot of confusion here. And again, and later, I did promise, like somehow if we all sit through this and stuff, somehow I'm going to put in a point portal so you all can get some points for sitting through this. You can remind me of that later. But anyway, right now I'm saying, okay, here's our example. Say our example is some mass at the end of a long string that is free, and the string is hooked at the top. So the string is free to act like a pendulum, and we're watching the mass as it swings back and forth in a pendulum arc, and that's our situation. And let's imagine that someone is asking us to draw a free body diagram of some moment amidst this swing. Like again, now remember, when we are asked to draw a free body diagram, we're going to pick some point in time, we're going to pick some point in space, and that is occupied by the point mass in question. Right. So this thing that I just drew here is a picture of the situation. This is most definitely not a free body diagram. This is a picture of the situation that we're being asked to diagram. This is more like a sketch, I should say, sketch. Now, even in the sketch, there are some good rules to follow and some rules not to follow. Like even in the sketch, it's pretty important that you label every quantity that's ever going to be used as a variable or a constant in every equation that you write. Like that's actually kind of the idea of a sketch. But still, okay, it's an informal sketch that's meant to show us what's going on, but also to kind of give us a hint as to how our coordinate system is going to be set up and stuff like that. Like here's a sketch. So it's a rough sketch. So it has like the little wind indicators back here, and it's not formal, but it is showing you that the way I'm picturing the situation is that an object is like somewhere displaced from an object on a string is somewhat displaced angularly from the vertical orientation of the string, and right now at this moment that I'm watching it, it's about, it's amidst a downward swing to the left on the page, or in other words, like clockwise on the page. Right now, that's the sketch. If I say, so here we go now, if I say that I want a free body diagram of this object, of this mass, the mass that's on the end of the string, and I want the free body diagram to represent what's happening right now, okay, I'm going to start getting technical now. Like, again, I know I'm pretty much probably boring I know everybody pretty much knows everything I've already said. That's the big picture. But now, if we're going to get technical now, especially since I took off points and all of that, if you're in a physics situation, or like God forbid, you're in graduate school or something like that, if you're ever in a physics situation again and someone just asks for a free body diagram, if they don't specify any further, if they just say free body diagram, the assumption is that they want what we might call in this class, or what many people call a pure free body diagram. Like the first thing to draw is the pure version of the free body diagram, which is to say exactly what I wrote 2 pages ago in these notes, is just to draw a dot, and draw one arrow for every force acting on that dot, right? So here I am dragging this out now, but this is, so if this is going to be a pure, Okay. I'm still stalling here for a second because this is the, okay. First of all, again, I'm saying pure is the word that we use. We didn't make it up, but many classes, many schools, many textbooks tend to use the word pure to absolutely emphasize that nothing has been done to the free body diagram. No further computations or breakdowns have been made or anything like that. In other words, well, I'll get to that in a second, but pure, like if no one says pure, then the assumption is pure. Pure is just to emphasize the unadorned, untampered free body diagram. And please now, this is where we remember the only thing that a free body diagram is for, the super important, but only thing, or therefore single purpose thing that the free body diagram is for, is to reveal every single force, both the comparative magnitude and the comparative direction of every single force acting on our object. Like that's what the free body diagram is for. It is meant for us to be able to fill out the left side of F net equal MA so that we can calculate A. So let me start by, so in a free body diagram, there should be nothing but forces, nothing but forces. And if it's a pure free body diagram, there really should be nothing but forces, not even details about those forces, just the forces. So if we're in this example of this pendulum, like the first force that we always draw in every single free body diagram, this I know people know, although actually even here's where people started getting into issues on the exam, but the first force that I put in every single free body diagram, because it's always there in classical mechanics, is the force emanating from the center of planet Earth that we call gravity, or we call weight, or we mathematically designate, with mg. Like mg is the force of an object's weight, right? And it's understood that the mass that we're talking about is mass m, as was depicted in the diagram before, right? So in every single free body diagram, there's the downward pull of weight, meaning whatever object we have, the Earth is pulling down on it towards the center of the Earth, okay? And if we had a scaling factor or lots of things going on, like the heavier the object is, the longer this arrow would be. I mean, so far there's only one. I mean, I don't know what to compare it to, so I'm just drawing it, right? Now, we have to draw every force acting on the object. Nothing but forces, but we do have to draw every force acting on the object. Now, and here's the thing, like, how do we know the forces? I mean, if we actually knew them, would we really even need this diagram? Well, the diagram is the thing that forces you to account for the forces. The way to know what is acting on an object is first and foremost gravity, because it's always there. But after gravity, you only and always draw anything that's touching the object. And you draw an arrow that represents the direction of that touch. Right? And literally, it is that straightforward in classical mechanics. The only way to exert a force in classical mechanics is to touch something, unless you're gravity. And that's why gravity is like the grand exception to all. Gravity is such a focus of concern for so long in physics, because it's the first force we ever look at that happens without touching. So it mystifies us. We wouldn't believe in it at all. We wouldn't believe that it exists, or certainly we wouldn't call it a force were it not for the fact that it is happening all the time empirically, right? So we observe it, but it's very hard to analyze because it breaks every other rule of force that we have at this point. But anyway, so I'm now going to draw an arrow for everything that's touching the object. Well, what's touching the object in this case in the pendulum? It's the string. And I draw an arrow in the direction that the string is pulling at the particular moment in time and moment of space that we're talking about. Well, according to this picture, so this is where I need my picture, right? Even before I draw my computational tool called a free body diagram, I look at my rough sketch and I see, oh yes, according to the rough sketch, like the object is like over here to the right and above, the equilibrium point in this pendulum. So the string, according to this picture, is pulling up and to the left. So I stay consistent with this picture, and I draw an arrow going up and to the left. Oh, let me be even more specific. I draw an arrow going up and to the left. Now, if I firmly believe that arrow should be equal in magnitude to the other arrow, if I believe the two forces should be equal in magnitude, I would try hard to draw them equal in length. I actually don't believe that. I don't have active reason to believe that they are. B, I think with a little bit of experience, I have active reason to believe that they're not. But unless you literally actually believe that they're literally equal, you should just not make that assumption. So I'm not going to, I don't think that they're equal. Sorry, someone just came in. So I'm going to just draw them at random lengths to each other. So don't make this work. And this is not something I took. This is not where people lost points or anything, but so I'm just drawing it like at random. I'm just showing that they're arbitrary lengths. Like I don't know how their lengths compare. And if you were pretty sure that it should be the other way around, you could do the other way around. But the point is they're not equal. All right. That right there, that T, right, stands for the tension force in the string. The tension in the string. The string is pulling up and to the left according to my other sketch, right? And it's there. I know it's there because string is touching the object. And I know the gravity is there because gravity is always there. Nothing else is touching the object. So nothing else is in this diagram. Let me pause there for a second because already now we are at a realm where people did lose points or there was confusion. This is the pure free body diagram of the bob in the pendulum, like as in your midterm exam. You could also draw the T very short and the mg very long, like that, because you might not know until you do things like how they end up. You don't know magnitudes until you figure things out. That's understood. But the key point is that you don't. Well, one point about magnitude is do not expressly make them equal unless you explicitly think you already have that information, like unless it's already given or somehow really known that they're equal, because that's like too important to just assume. So I'm not here to get bogged down in the lengths of them, but I will say before I go any further, this is the whole diagram. And it's really important that it's the whole diagram. Like you might think, oh, that's all you wanted, Yaverbaum, or that's all that's supposed to go in the free body. Yeah, the fact that it's that simple is part of why it's that helpful and that important. In the pure free body diagram, well, let me back up. In any free body diagram, all that should be there is forces. Anything else, like anything else that, I mean, and you could maybe even, you could label the angle, I guess, if you want, and I probably wouldn't take off points for that, but if you start drawing in the length, like if you start drawing in the string length, or you start drawing in the ceiling, or you start drawing in other things or velocity or something like that. Now, wait, let me just look at it. Wait, if this is about, I don't want you to show, hold on, if it's about, no, wait, that's a fair question. I'm about to get to that. No, that's a fair question. I mean, Yabo's question is a fair question. As far as sine and cosine, those are called components, and I am about to get to that. That's called a component diagram, and yes, they become very important. And even if you put them here, I'm about to get to that. No, I'm not saying I never want to see the sines and cosines, but we have to be very careful how they put them in. So yeah, let me just pause. So yes, I'm going to get to that. But right now, what I'm saying is I definitely don't want to see a ceiling. I definitely don't want to see, I want to see if that upward, and I am being, picky, I know, but if this arrow is being labeled, it needs to be labeled like with the word T, I mean with the letter T, or the word tension or something like that. In other words, this arrow is being drawn because we believe it's a force. If we start getting into labeling this arrow as length of string equals 3 meters or something, that gets very confusing. And it gets like very confusing. It becomes unclear what it is that we're trying to depict or what we're going to do with this. This is supposed to be about forces. Really specifically, what I don't want to see here is acceleration or velocities or anything like that. Truthfully, I don't even want to see numbers. I just want to see names of forces. But now, so this would be one version of the correct answer to what's the free body diagram of the pendulum. However, now, this gets into not only Yabo's question, but what happened to a lot of people. This is a pure free body diagram. What good is it? What's the point? Well, yes, I keep saying that the point is this. I mean, and it is, right? The purpose of this diagram is that Newton's second law says on the left side, you got to add up all the forces acting on an object. And if you add them all up, then you'll know what the acceleration is of the object. But this law, Newton's second law, is, as you can tell from the symbols, is a vector equation. So it's saying something very particular. It's saying add up what it's really saying is, like every vector equation, every two-dimensional experiment, or every two-dimensional equation, or every two-dimensional problem, remember, is really two one-dimensional problems or two one-dimensional equations occurring simultaneously yet independently, right? I mean, and again, this is where I'm going now. This is where Yabo's question is going to come in, and this is where more details come in. We're using this, we're making this diagram to be able to apply Newton's second law. Newton's second law really, when translated, if we understand vectors, what Newton's second law really says is something like this. Or before I go any further, I just want to remind us all, like, and again, all of this still boils down to Galileo's principle of relativity, right? All of this still boils down to the laws of physics are the same in every inertial reference frame or in every coordinate system, right? That's why we're allowed to say, I mean, the laws are the same no matter what your coordinate system is, no matter whether you look at things like this, or you look at things like this, or you're looking at things from 100 miles an hour, or you're looking at things from 200 miles an hour, as long as your coordinate system is not accelerated, then the laws of physics are all the same, which means we both can, but also must always choose our coordinate system before we do anything further in physics. Like, we have to choose a perspective or a reference frame or coordinate system that will conveniently allow us to solve problems. Like, the power of physics is the problems can be solved from any perspective. But the responsibility of physics is then you have to choose your perspective and remain consistent with it. First of all, if you just drift away from your perspective and are not consistently solving a problem in one perspective, you'll get things wrong. But number two, you get different answers in different perspectives. So you have to know what your perspective is before you go any further. So what I'm saying is this: that applies to coordinate axes. The laws of physics occur on this axis at the same time, but independently from the way they occur on this axis. So when we say F net equals ma in all of space, we really mean F net equals ma along each axis independently and simultaneously. So we start breaking down problems and looking at two-dimensional problems as pairs of one-dimensional problems. Well, so when we say F net equals ma, I can say, well, it's true on the X or it's true on the Y. But of course, first of all, I could call this X and call this Y. It doesn't matter what I call them as long as I call them something consistent. Or also, I could look at this axis and this axis as you do on an inclined plane, right? On the inclined plane, for example, you divide things into two coordinate axes, but you don't pick X and Y. You could, because the laws are still the same, but all your calculations are much, much, much more difficult if you try to analyze an inclined plane along this and this, rather than tilting your axes to match the plane. Same thing here. We can say the Newton's laws apply on X and Y, or we could say they apply on X and Y, or we could be even more clever, since this thing is going to be traveling in the arc of a circle. We could impose axes that have to do with the radius of that circle and the tangent line to that circle. We can do whatever we want, but we have to do something, and we have to know what we're doing, and we have to do it consistently, right? So what I'm saying is, what happens, and again, this is to Yabo's, I mean, this is the next stage of this, like whether Yabo's asking or not, but I'm saying this is a pure free body diagram. If anybody ever just asks you for a free body diagram, all you should do, or all you need to do, is just itemize the forces in this way. But then if you want to start doing calculations, then you want to start dividing these forces into components. That is absolutely true. And most of you understood that and realized that you would have to divide these forces into components in order to start calculating accelerations and stuff like that. All true. So you have to divide forces. But what does it mean to divide forces into components? It means choosing a coordinate system, choosing two axes specifically, and saying any forces that are not along either of the two axes of your coordinate system have to be divided up. Like Let me back up for a second. So I'm totally going to do it. And I'm still not saying, I'm not saying this is the only way you could have gotten full credit. You'll see in a minute that you still could have gotten full credit on the, you, whoever, all of you are. This is technically is the pure free body diagram. And this is the safest thing to do because like there's no choices to be made here. We're just drawing all the forces that exist. But now so what I'm saying is, okay, I'll just give you a chance to, so this says, so I'm going to go to the next page in a second, but it says, if this page says, if and when we wish to start computing with our forces, okay, and of course that is the point. We've drawn this diagram so we can start actually doing, we can start adding together the F's in order to get the A on the right side of F net equals ma. So if we want to start computing with those forces that we just identified with the pure free body diagram, then we have to recognize, okay, the F net equals ma only applies to each axis independently, yet simultaneously, right? So yes, we're now going to, well, so then we must recognize that F net equals ma applies to each axis independently, yet simultaneously. Okay, so now comes the part which a lot of people did do on the exam, and this is a right instinct, but this is where I know something is confused or backwards here, or I believe in many cases. So what happens now is like that's our pure free body diagram I just drew over there, just the two arrows. That's simple. It is showing what things are pushing or pulling on our mass. Now, in order to do calculations, what we absolutely can and absolutely should do is say, okay, wait a second. I recognize that F net equals ma only happens one component, one axis at a time. So I look at my diagram, I look at this diagram and I say, oh, this is a problem because F net equals ma says to add up all the F's, but I literally cannot add that T to that mg because they're not happening in the same world. They're not happening along the same axis. Like they're not affecting each other directly. Kind of like all the way back to lab 3 of physics 203, if you were in that course at John Jay, that thing where you draw a bunch of, where you're trying to get off an island on a piece of graph paper and you have a bunch of arrows trying to get you off that island on the graph paper. And what people realize in lab 3 is like, oh yeah, you can add up a bunch of north pointing directions and they cancel out with all the south pointing directions. I don't want to get into the whole lab right now, but like people realize pretty quickly in that lab, oh, the direction, the displacement 5 units north cancels out with 4 units south, and it just gives you 1 unit north. They realize, you guys realize that, and you're right to realize that north and south just kind of like cancel out with each other, and norths and norths accumulate, like 5 north plus 7 north gives you 12 north, and 2 south plus 1 north gives you 1 south, etc. But the converse of that is that 3 north plus 2 east doesn't give you anything like that. North does not communicate with east. It's 2 different coordinate axes. It's like 2 different coordinate systems. It's 2 different inertial reference frames. They don't communicate with each other. The only thing that communicates are, so when I look at these 2 arrows, the first thing I would say is I can't add this T to this mg. I cannot plug these both into the left side of F net equals ma. And then someone might say, well, can't you use a minus sign? Can't you say like T minus mg? Well, no, I can't even do that because T is not communicating with mg. They're not on the same axis. So then what I know, and this is the part that I'm dragging out because this is the part where I think there's confusion. Well, no, I'm dragging everything out because that's what I do. But here's the part where I really think there's confusion and of the sort where people think they know, but they don't know that they don't know. That I think many of you realize at this point, okay, I'm going to divide something up into components. I think many of you say to yourself, okay, I'm going to divide something into components, and that's what Yaverbaum wants, or that's what the problem needs. I'm going to start introducing sines and cosines. And then some of you even realize that you might even have some confusion of which gets a sine and which gets a cosine, or which thing to divide up. I think some of you don't even realize that you're confused about that, but whatever it is, and I'm not saying this critically, and if I sound all hyped up, it's actually about something else. I promise I'm not really upset about this, but I do think it's important. I think a lot of you at this after you see a diagram like this, you start immediately thinking, I better divide something up into sines and cosines. And that's true, but you're already skipping a step if you say that in your mind. If you're thinking about what should I divide up, or which should be sine and which should be cosine, the first question to ask is, what's my coordinate system? Instead of asking, should I divide up mg or should I divide up t? Because the fact is, depending on you could do either one as long as you're consistent. The question of which one, like both would be right. I'm not both. You can't do both. But you could either divide up mg into sine and cosine, as some of you did, or you could divide t into sine and cosine, as some of you did. And actually, either one will work if you only do one, but you have to know what you're doing and you have to know why, and you have to stay consistent with it. So instead of asking yourself, which should I divide up? First, you have to ask yourself, what's my coordinate system? Anything that's not, well, yeah, I'll write this down, but the point is that anything, you pick a coordinate system, like you ask yourself, what are the axes here? And anything that's not lying along an axis is what's going to get broken up. So it's really the inverse of the thinking that I think a lot of you are doing. It's not a question of which is the special force that I should specially break up. It's really which are the special axes, and whichever force is not lying along the special axes, they are like the bad force, the annoying, inconvenient force. That's the one I have to break up. So let me just, hold on a second. So first, Okay, this is the part that, again, I think this is the step that may be being skipped, or maybe people didn't ever realize they were doing this, or what, or whatever. But like, first, we're choosing a coordinate system. We're choosing it to make F net equals ma as easy to solve as possible. So what it really means is we're first going to choose. I'm looking at the time. Oh wow. Okay. Well, this is taking. Okay, but we'll, at least we will be done with this before the end. Sorry. Um, we choose a coordinate system. That means, well, and again, any coordinate system will work if we're really, really super careful, but some will be a lot easier to work with than others. And none of them will work if we are in it unconsciously or inconsistently. So we have to consciously choose a coordinate, like a set of axes, and we have to consistently stay with that. The convenient strategy to pick will be the convenient strategy that has as few sines and cosines as possible. The first time we ever saw this occur is way back with the inclined plane in physics 203, where if you think about it, the first time we ever started like dividing mg into sine and cosine, and it's very confusing when we first do it. It really throws people. And the way a lot of people get through the inclined plane is they just blindly memorize that mg sine theta is along the plane and and they move on with their lives. But they know they've blindly memorized because they know something got weird for a minute when all of a sudden mg, which was straight down, got divided into two like legs. Like, remember that in the inclined plane, the pure free body diagram was normal, was exactly like ours here. We had normal force pointing up at some angle, and we had mg pointing straight down. And if you remember way back to the inclined plane in physics 203, we had a diagram that looked just like this. Sorry. And I am aware of the time. We had a diagram just like that, only it was normal force rather than tension. And then, even though gravity was pointing straight down, and it really would have seemed reasonable and typical for us to say, oh, the normal is up at this cockamamie like diagonal angle, so let's break it up into sine and cosine. We instead broke up mg into sine and cosine. And that's a strange thing to do. And it's so strange that I believe that what a lot of people did was they just accepted that and moved on with their lives after they got over the initial confusion. But the reason we did that, is because F net equals ma, and the object is going to accelerate down at an angle. So we deliberately chose a coordinate system. We lined up the graph paper of our mind with the inclined plane and said, aha, let's make it so that the x-axis is along the plane, because the object is going to accelerate along the plane. And we don't want to have to say F net equals ma sine theta or F net equals ma cosine theta. We want there to be acceleration along the x-axis, and we want no acceleration along the other axis. That's how we could like set the two forces along the other axis equal to each other, because we don't believe that the block is accelerating off the plane or crashing into the plane. But that means we were setting things up so that the block had no acceleration along that, what we ultimately call the normal line. And we set it up so that it had full acceleration along the diagonal. In other words, we tilted our coordinate system to match the acceleration of the situation. We line up our principal axis with the expected direction and line of acceleration, so that we can plug all of our sines and cosines into the F side of F net equals ma, and not have to have extra sines and cosines on the right. Like, no matter what, we're going to have to break up something. No matter what, we're going to have sines and cosines in our picture. But if we don't choose our axes correctly, we're also going to have sines and cosines on the A side. We're going to have way more sines and cosines and a lot harder of a calculation. So what we always do is, and I know I'm running out of time, I'm really running out of time. But so what I'm saying is we choose an axis that is parallel to acceleration. And in this case, we have something moving in an arc, and anything moving in the arc of a circle is always necessarily accelerated along the radius toward the center of the circle. That's called centripetal acceleration and all that, right? So we know that line of tension is actually an axis of acceleration. So we line up our axis with that in our mind. And even though I only have 2 minutes, this is a long way of saying that. And here's where the points got lost and all that. If we want a component diagram, thus this, and please stay with me. I know we have 2 minutes, But again, this will actually answer Yabo's question. And this is where I'm saying, if you want a component diagram, I have no problem with that. Of course, it's going to make your calculations easier. It's great if you give me a component diagram. But if you give me a component diagram, here's the component diagram. The component diagram would be the tension is still going up like that. And now gravity is split into two components, right? Which turn out to be mg cos. I'm not even analyzing right now why, which one is which. Maybe I can do that next time or not. But I'm saying this, if you give me this component diagram would look, if you gave me that picture with 1 minute left, if you gave me that on your exam, T and mg cos, mg sine, that's full credit, that's fine. And again, to answer Yabo's question, I know I'm spending so much on this, I want to be as clear as possible. That technically is a component diagram, not a pure diagram, but it's fine because it is more useful. It's totally fine. If you just gave me that on the exam, that is fine. That is full credit. But where almost everybody who did lose points, lost points, is you cannot give me, and I know I'm yelling, but just to be clear, and I know this sounds really picky, and this also why I'm spending an hour on it, because you never know, I guess, when I'm going to be picky and when I'm not. But if you put mg and mg cosine theta and mg sine theta in the same diagram, that's when I went bananas and took off 2 points or something, because then you're in effect telling me that gravity is acting twice. And I'm not trying to be picky, but I am. Like, you either give me mg, or you go to the next step and you break up mg into its two components. You either give me the whole or you give me the sum of its parts. But if you give me the whole and its parts, you're giving me the whole twice. And this whole thing is, and if you give me anything else, I definitely took off points. All we want here is an accounting of the forces, either the actual forces, which then enable us to do this picture. See, and now this picture, now we can plug into F net equals ma, once on one axis and once on the other. Like, this is now computationally powerful. You could give me either one, but you can't put them both in the same diagram, because then first of all, it double counts gravity. Second of all, it really shows me, I think, that you've just memorized things and you don't really know what's going on. I mean, whoever you are, or it raises that question. Okay. So sorry to be ranting and raving and all that. And I will give you some more points now that everybody's just sat through this for 75 minutes. But what I'm really saying is, as far as the exams, I would take the other diagram that's like 5 pages back, or I would take this one. This is full credit. This is fine. But yeah, if you also have an mg arrow in here, that you can call me picky, and I will, I apologize to your God and my God. But yes, it was not a mistake on my part. It might just be cruel on my part. If you had mg and the sine and the cosine, then that's 2 weights, and that's too many forces, and and then you've also defeated the purpose of dividing into components, because then you still can't put that into F net equals ma. All right, sorry, I'm yelling. I know it's 1:31. Thank you all for listening to this. I'm just going to go before anybody cries, before I cry. Thank you very much. Okay, I'm literally going, goodbye.